Hi guys, and welcome to week 5. So in this very important video, we will talk about what's happening. So this is a typical week. I mean, we still have our discussion boards due Wednesday, homework due Sunday. No quiz this week because you just wrapped up a quiz for the last 2 weeks. And this week you will see the big ticket. It's posted and it's due on October 22nd. So I'll talk a little bit about that here. You can find your group, and I've tried to pair you up accordingly. So groups can be found by following the instructional document in Canvas. I'll show you where that is. That'll help you locate your groups. There should be a group tab off to the left of your Canvas screen, although I can't see it in there in mine because I have the instructor view, and so there are certain things that I can't exactly show you or demonstrate from my position. So when you're working on this is a group project, small groups. About 3 people per group, and it's up to you how you want to approach this. You can meet physically if you want to meet on campus, or you want to meet at a coffee shop to work on things. Great. If you want to start a Google Doc, and if you just Google how to start a Google Doc, you will get plenty of information on how to do so. And that's a way that you could all network and access the document, edit the document from different locations, and be able to track what everybody has done to the document. You can use Skype or FaceTime or whatever works. I'm sure there are many other services out there that I don't even know about. Or you can correspond via email, phone, text, whatever works for you. So for everybody, this is going to be different. But the key here behind this big ticket assignment and making it a group project is that in the real world we are forced to collaborate and communicate. Now, even as an instructor, you'd think that I just teach in a classroom or teach online. I'm just on my own. Well, I serve on different committees, and I am expected to work with others, and so this is an important skill, especially in today's day and age where it's so easy for us to hide behind computers. So when you are working on this, keep that in mind, that this is preparing you rather than torturing you. Hopefully you'll be able to look at it that way. And that once this project is assigned and due, be working on it on a regular basis. Don't wait until the last minute. Waiting until the last minute is the easiest way to not succeed. So be working on it throughout, because there's a reason I give you this much time to work on it. And so I'll leave it at that, and I'll just keep kind of emphasizing these ideas. So this week you will be looking at a discussion board entitled Exponential versus Linear. And in this discussion board, you'll be kind of focusing on, well, now that we have 2 functions, how do we pick the right function to model the data at hand? And this week's content will be focusing more on modeling with exponential functions. So lastly, I'd like to go ahead and wrap up the discussion board from this previous week. What's in a linear model? And we were given this set of data here, these set of 4 ordered pairs, which in the real world we usually have a lot more. But to keep this simple, we're looking at people's age and their corresponding income, and these are in thousands of dollars, and that's a yearly income. And so we want to fit a model to these data points. Now, if we go and plot them, which I have done over here in wrong page. I have done that here. I've plotted my data points, and I have no reason to suspect that there isn't a linear trend. Although if I tried to fit a line, I could see that line probably would not naturally go through all of the points. But nonetheless, I don't have any reason to believe that there isn't a linear trend. Data doesn't fall perfectly along a straight line, even when we determine there is a linear trend. So then we need to figure out what to do. Well, one way to do that is to just start to look at the slopes. And I've done that here by looking at the age, the income, and this block here is actually the slope between these 2 points. Just an easy way to kind of keep track of this stuff. So we have the difference in income, which is about $14,000 for an age gap of 10 years, or an increase in 10 years of age. So we see that on average, a person between 20 and 30 years of age has an increase in their income of about $1.4 thousand per year. That's $1,400. And now, is that always the case for everybody? Well, of course not. Some people are unemployed, and so are not working from one year to the next, or are doing other things that don't require direct employment on a payroll. Or, of course, some people climb up the salary ladder much faster than others or much slower than others. So similarly here, we can look at the rate of change between a 30 and 40-year-old, and we see that between those two ages, on average, a person seems to gain almost $2,000 a year in income. And between these two ages, we see about 1.5 thousand. Now, this is only based on 4 ordered pairs, so this is definitely not enough data. But based upon this, I can even see in the rate of changes that they're approximately around, they're sort of circling somewhere around 1.5, 1.6. Well, let's figure that out for sure. So we take the one way we can approach this, sort of intuitively, is, well, if we're trying to look for the best slope, maybe we take the average of the 3 slopes. And so we get approximately 1.6, or on average, between the ages of 20 to 50, roughly over those age blocks, we see about an increase of $1.6 thousand per year. So far I know that I can model income as a linear function. I know that the rate of change is 1.6. I represents the income, the output, and I know that I'm going to need to multiply that by the age. However, I need a vertical intercept. Every function needs a vertical intercept. I can't just ignore that and say 1.6 times your age, because 1.6 times 20 would be 32, and clearly that's very far off from the income here. And similarly, 30 times 1.6 would be 48, and 33 is much lower than 48. So what I can do to solve for this is that if I can find a pair that corresponds age to income, then I can estimate this value of the vertical intercept. Now, it doesn't always make sense, keep in mind, because that would correspond to a person who's age 0, and what would their income be? Well, if we use the first ordered pair, 2019, then and we substitute and solve for the vertical intercept, then we get negative 13. Well, that clearly doesn't make any sense, because a 0-year-old doesn't make negative $13. We don't try to interpret that. And let's think about if I had picked a different ordered pair. Why did I have to pick that one? Well, maybe we argue that that's the age that's closest to the vertical axis in terms of horizontally. But I could have picked 30 and 33. And then I would get a b value, a vertical intercept of negative 15. And if I had yet even picked the next ordered pair, this one here, I would have had a vertical intercept of negative 12, or 0, negative 12. So why is this happening? Well, this happens because these points are not all along a straight line. If they were, then we would get the same vertical intercept. If I had these data points and they were all along a perfect straight line, then the vertical intercept that I would get by using, this is going to be very hard for me to draw because I'm using my mouse here, but hopefully you get the idea that if I drew a line, that's very bad. I'll stop there. If these were along a perfect straight line, they would all run through the same vertical intercept regardless of which one I would pick. Okay, well, what's the quote-unquote right technique here? The right technique, or the one that we use most often, is called linear regression, which you learned about in your course content this last week. In statistics or mathematically, this is often referred to as the method of least squares. So let's say we fit a line to some data points, and we have our data points here, 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 and here, and we see that they don't fall along the line of best fit, or the linear regression line. But so at every single value of x, for example, at x equals 1, we can see that our ordered pair is above our estimate that we would get by plugging that x value into the function representing our line. So that means that this here, right there, that's an error. That's that difference between what we actually have and what we estimate based upon our model. That is considered error. That difference there is considered error. Same thing here. The point that I would get by plugging in x equals 2 into my function is higher than my actual y value of the ordered pair in my data set. So again, that's error. And same thing here, and same thing here. So why do we do this then? Well, what we're trying to do is take basically a mess of data, something that has a cluster of data everywhere, and we're trying to organize it and pick something that best models that data. So think about how we find an average. Why do we find an average? We try to represent the data set by saying, yeah, if all the data points were the same, here's what they would be. That's the value of the average. We're trying to sort of do the same thing here. Now, what I'd like to do before we wrap this up is finally, let's take a look at the 3 lines we came up with. that's 1.6x minus 15 using the first ordered pair. And we see that that's pretty good, right? We see a little bit of error here, a little bit of error here, a little bit of error here. Doing pretty good right there. If I take a look at the next line, let me just remove the first one. I feel like that's even a little bit better, right? That it goes through or seems to be fairly close. It's hard to tell whether it goes exactly through those 2 points. But we see that these 2 points, a little bit of error here, but quite a bit of error here relative to the, well, I guess we had a lot more error here if we added up those errors. And with 1.6x minus 12, we do pretty good. So which one's the best? Well, it's kind of hard to say, right? This method of least squares, when we use this method of least squares, what we do is we add up all of these errors. Well, excuse me, we find the errors, we square them, and then we ask what is the way that we could find the correct slope of the line so that we get the minimum error, the minimum squared error. Don't worry too much about how exactly we would do that. But let's say that I wanted to model the slope and y-intercept and kind of pick the best one that I could think of. So I could change the vertical intercept here, and all I did is typed in y equals mx plus b, and it asked me to insert some sliders and change the slope. Obviously way too big, lots of error there, so I can kind of tweak that, right? But the problem is when I think I have a good slope, now I can also change this other thing. So where should that line be exactly to minimize the sum of the squared errors? Well, that's a little bit better. So maybe if I change the slope a little bit more and lower that, maybe I need to come over here. But anyway, we can kind of play around with this. And the question is, how do we find the best line of fit? Well, again, the method of least squares is the method that we use. Is it right? Well, just like anything is considered right, it's subjective, but it's the thing that we use most often. I'll stop there. Have a great week. Look forward to seeing you in the next discussion board. And again, check out those projects.